Hi, I'm Joe Battistelli. I'm an instructor for quantitative biology, and I wanted to make this video about how and why we do graphs in the sciences as a means of summarizing and presenting data. It should help you guys out with your graphing assignment. Let's get started. So we're going to be asking ourselves, why are we going to do graphing? What is that really going to tell us that we can't get from just looking at the data? And there's really two main reasons, three really. We want to visualize our data, and we're going to want to summarize our data. And what does that mean? Well, if we have a data set that's enormous, we can't just look at a table in Excel or something like that and be able to analyze or interpret that data. So we really need to make a graph out of it so that it's visible, easy to see, and easily summarized. And this is going to let us compare different kinds of graphs or different data or different samples, different populations, maybe different treatments in our experiment, or see how a population responds to change over time or some other changing factor. So what are two main kinds of graphs that we're going to be talking about? Well, first of all, we have some graphs that let us display variation within a population. So we're looking at one single factor or attribute of a population, and we're going to see how that population varies. Is it all really big? Is it all really small? Are they all about the same size? We're looking at one attribute about this population. So what kind of graphs would we do that with? Well, we could do a box plot where we're just going to look at data. It's going to show us our average, standard deviation, maybe some outliers. So we can learn about the spread within our population. We might also do a histogram. So that's another one where we're going to have groups within our population, and we're going to have frequency of occurrence for each member that's a certain size or a certain color or some attribute. So histogram, again, is going to give us a sense of what this population looks like. And then another kind of graph for doing this, where we're going to look at one attribute within the population, is cumulative distribution function or graph, where we have one trait on the x-axis and then again frequency on the y-axis. Again, only one trait and only one population. So eventually we're going to need to do a couple different kinds of graphs in order to look at multiple variables at the same time, or to look at two populations and compare them to each other, or to look at change over time or some other variable. So we have a couple different options in order to accomplish this. We could do a line graph, and commonly what we do is we put our independent variable x, often time, on the x-axis, and we put our dependent variable or our response variable on the y-axis, like size over time, and we see that whatever we're monitoring is growing and then reaching a plateau where it straightens out. Another common thing we do is we make a scatter plot. So again, we'll put one variable on the x-axis and another variable on the y-axis, and we'll look and see how these two things respond to each other. Is there a relationship? And in that example, we saw there was a linear relationship. X went up and so did y. Another common type of graph that we'll make is a column chart. And Excel, and scientists usually call this kind of chart a bar graph, even though it's called a column chart in Excel. So we'll put our response variable again on the y-axis, and usually we'll end up with some sort of categorical variable or treatments in an experiment on our x-axis. And we'll have treatment A and treatment B, and we'll see how they responded. And treatments could be antibiotics, or some other drug treatment, or fertilizer. Maybe treatment B got nitrogen fertilizer, treatment A was our control with no fertilizer, and we see that treatment B grew much larger than treatment A. So bar graphs really let us compare two treatments or more. So these are just a few of the ways that we can graph and compare different variables or different populations. Here we are in Excel, and we're looking at the salamander dataset from your graphing assignment. If we look at the first column, this is just numbering all the individuals in our 3 different salamander treatments. We have a high water treatment that received plenty of water, a low water treatment that received the minimum amount of water required for growth, and we have a dry down treatment where the salamanders were allowed to completely dry out in between sampling times. So what I've done over here is I've copy and pasted the dry down column, and I use the sort feature in order to sort the data in ascending order, so going from smallest to largest. And then over here I made 3 groups of sizes, the size between 18 and 19. I'm sorry, not size. This is days until metamorphosis. And I did the frequency for each of these time periods, between 18 and 19 days, between 19 and 20, and greater than 20. And then I used that information to make a histogram about the salamanders in the dry down treatment. But as you can see, this histogram that we just made doesn't really help us compare the dry down treatment to the low or the high treatments. So what we're going to walk through is going to be how to make a more comprehensive graph where we're going to make a bar graph, a column graph, in order to look at these 3 different treatments and compare them. So let's get started. So the first thing I'm going to want to do is I'm going to need to know the average and the standard deviation for each treatment. So I'm going to use a function in Excel so it's really easy to calculate it. I just do the equal sign, the function is average, and then I'm going to highlight all the samples from that treatment and get an average. And then I can do the same thing in the other cells just by copying and pasting that formula over, and it'll automatically change to do the other columns. So that's the average, and now I need the standard deviation, and that's just STDEV, and then I'm going to highlight the data. There's my standard deviation, and I'm going to do one more thing. I'm going to make standard error, and that's just going to be standard deviation, so I can highlight this cell, divided by the square root of the number of samples. So in this case, the number of samples was 30, and to do a square root in Excel, I raise to the inverse exponent. So you can't write square root, but what you can do is raise to the power of 1 over 2, and that's the same thing as taking the square root. So that's standard error, and I'm going to do that for all 3 treatments. Now I want to make a graph, so I'm going to go to charts, I'm going to go to column chart, and I want to do clustered columns. I'm going to go right click on it and then select data. I'm going to add one series. So I'm going to do X category labels, and these are going to be our column titles, high, low, and dry down. And then I'm going to do Y values, and those are going to be the averages that we calculated. Oh, that worked. Cool. So now we're still left with this. Well, for one thing, I hate these horizontal lines, so I'm going to get rid of them. I'm going to change the color to no line. It can go away. And then I need to add error bars. So this is probably the trickiest part of this whole process. I'm going to right-click on them, and I'm going to format data series. And then error bars. Now this is set for Y error bars, and that's what we want. I'm going to add them up and down, and I'm going to do custom error bars. I'm going to specify the value, positive value. So what I did there is I clicked this little thing, and then highlight the standard error in the positive direction. And I'm going to do the same thing for the negative direction. Click OK. And OK. We have really tiny error bars. So that is important because that lets us see that our data is really reflective of the population. If we had huge error bars, we would suspect that there was a lot of variance within our population. But since they're really tiny, we know that our average is really reflective of the whole population. Further, since our dry down column is very different than our low treatment and our high treatment, and the number of days it takes for the salamanders to metamorphose, it's very likely that if we did a test for significance, we would see that this dry down treatment was significantly different. And we can tell that because these error bars don't overlap. They're more than one standard deviation or more than one standard error apart. And that tells us that there's a very high likelihood that these two things are significantly different. So that's what we want to see if we want to see a treatment is significantly different than your control. So you want to see a difference greater than the error bars. And that helps us standardize between a population with a lot of variance. Well, if those error bars are huge, then we know that they're not really, the two treatments aren't really different. But if two treatments still have an average and the error bars don't overlap, even if that average has a huge variance, we would still expect there to be a difference. So let's look at one other kind of graph. We're going to do line graphs. So in these graphs, we're looking at two bacterial species. We've got exponential growth of Mycobacterium sphygmatis and exponential growth of E. coli. So let's go ahead and make this E. coli graph over again. So what I'm going to do is I'm going to go to charts. Oops. And I'm actually going to do a scatter plot. It's a little bit different than you might think, but I'm going to do a marked scatter plot. And then I'm going to select data just like before. I'm going to add a series. I'm going to do the Y bacterium, and we have E. coli's abundance for our Y data. And I put that in the wrong block, so I'm just going to do Control X. I'm going to paste it where it should be. And then I'm going to go back and do time in the x-axis. Plot, and I'm going to hit OK. So just like before, I'm going to get rid of those because I don't like them. And now I'm going to format the data series. I'm going to add a line in, black line. And then the next thing I'm going to want to do is I'm going to want to do this thing called adding a trend line. So if we add a trend line, it's going to let us display an equation for graphing that line, and it's going to let us see the r-squared value. So that'll tell us how good a fit this line is for our data type. And we already know that we are going to have exponential growth for our bacteria. So I'm going to change the trend line type to exponential. And now we can see that we have a really great fit for our data. So our microbial growth line, our microbial growth is accurately represented by our trend line, this equation right here, and r squared is even equal to 1, which strongly suggests that I made up this data for you guys. Okay, that is all for graphing. These are the kinds of graphs you're going to need to make for your graphing assignment. I am using Microsoft Excel on my Macintosh. I think it's the 2011 version. If you're doing this on a PC or a different version for Mac in Excel, it's going to look a little bit different in every version of Excel, but the keywords are the same. So you're always going to be right-clicking and adding the trend line or formatting the trend line, or right-clicking the graph and adding the data set. Some people even highlight the data before they start and then just tell it to make a line graph, and it'll make it. You can do that. I find when I do this, I tend to do it wrong and basically have to delete all the data and start over as if I were just making a line graph and right-clicking. Key difference between a line graph and a scatter plot. Line graph, you don't have the option to add the trend line, whereas with the scatter plot, you can add in the trend line. So I usually make scatter plots so I can add in a trend line and see if my data fits a standard linear regression. Cool. Good luck on your graphing assignments.